Hello, in this lesson, I'm going to review chapter 6.2, the binomial distribution. Note that the binomial distribution is one common discrete distribution. In chapter 6.1, we learn discrete distribution. So this is a special case of the discrete distribution. To be considered as a binomial probability experiment, we had to satisfy four conditions, right? So the first one is there are fixed number of trials, and let n be the number of trials here. All the trials n are independent. Number 3, each trial there are two possible outcomes, success and failure. Number 4, the probability of success should be the same for all of them. Here we're going to let p be the probability of success. Alright, let's do an example. It's known that 40% of transplanted trees survive the winter. If 3 trees are transplanted, what is the probability exactly 2 of them survive? First of all, let's see if this is a binomial experiment by check the 4 conditions. Okay, n, there are 3 of trees going to be transplanted, so n is fixed. We have 3 trees, and whether the first tree die or not doesn't change whether the second tree going to die or not. So the trials are independent. For each trial, each tree either survive or not survive. The survive considered success. The not survive will be the failure. So the 2 possible outcomes. Probability of success, in this case, is probability of survive, which is 0.4. So the all 4 conditions are met. So this is a binomial experiment. Okay, before we calculate the probability, we call in chapter 5, we can use the tree diagram to find, to list out all the possible outcomes to have 3 trees. Okay, so the first tree could have survive or failure, meaning the tree survive the year or die, right? So this is the outcome for the first experiment. And the second branch, this is the second over here. This is the outcome for the second child, which is second tree. The second tree could be survive or could die. So we could have survive, okay, survive and die, the second tree, right? And the third branch here is the third tree. You can think about it as a third tree. So we have 3 branches because we have 3 trees. The n equals 3 here, right? So let me erase that. So this is n equals 3. Okay, having exactly 2 of them survive, that means I could have SSF, SFS, FSS. Notice that all this are actually reading from the tree. Note that the first one is SSS, which is my first one. The second one is SSF, which is SSF. That's how I get the answer here. Let me highlight the branches, how I get it. See, this is this one here, the SSF, right? And this was SSS. That's the one I wanted. And I want 2 success, could be also this one here, 2 success. Okay, that's how I get the exactly 2 success here. So there are actually 3 ways of having 2 of them survive. Well, the number of ways that we can have 2 of them survive, 1 die actually is called combination in math, right? So if I want to find 3 n equal to 3, if I want to find how many of them survive, x equal to 2 in this case here, let me write it. X equal to 2. I can using a combination to find it. It's called combination. So if I would do NC2, NCX, in this case is n is 3, 3C2, I will get 3 as well, right? You can use your calculator or you can calculate it. To calculate is n factorial, which is 3 factorial, over 2 factorial, which is x factorial, and then 3 minus 2 factorial. Right, to calculate by hand, you could do that. That is 3 times 2 times 1. 3 factorial when you multiply all the way down to 1. 2 factorial means 2 times 1. 3 minus 2 is just 1. 1 factorial is just 1. So therefore, I can simplify it. 2 cancels out. 1 cancels out as well. 1 over 1 is just 1. So the answer is 3. So there are 3 ways to have exactly 2s and 1f, which is as we list over here. Right? 3 ways of getting exactly 2s and 1f. Alright, let's see if we can find the probability. Well, probability of having one of them is SSF, meaning the first 2 survive, the third one die. So if I would find the probability of SSF, that is equal to probability of success is 0.4 times 0.4 and times the third one is failure, which is 0.6. That is equal to 0.4 to the power of square times 0.6, and that is equal to 0.096. Notice that this is the first one. The second one, I will have probability of first one survive, second one fail, and then third survive, right? So that means I still have 2 S and 1 F. So the probability is still the same. I still have exactly 2, let me write it, 2 success. So S, F, S. Notice that I still have 0.4 times 0.6 times 0.4, and that's still 0.4 square times 0.6. So it's still 0.96. 0.096. All right. I think we can see the pattern. Using the same pattern, I can see that probability of F S S. It's still gonna give me 0.4 square times 0.6. I think we can see the pattern here. Let's see what kind of pattern we can come up with. Notice that 0.4 is my P. P is the probability of success. So notice that here I just have P squared. And 0.6 is just 1 minus P, right? So that's 1 minus P, which is 0.6 to the 1 power. So for each one of them, I have the same thing. P squared, P is 0.4, 1 minus P to the 1 power. So this is P times 1 minus P. So in general, to find the probability here, it's just P to the X. Let me write it. P to the X, and then 1 minus P to the N minus X. So notice that this is your X. This is the N minus X. N is the 3 here. So that's a formula to finding one of them. But there are 3 of them total. So 3 times that is going to give me the total probability, with the total probability of all 3 of them. With a number of ways to get exactly 2 success and 1 failure. So this is the general formula. Right, so that's again, which is what we found here. So notice that the first one here, this is the number of ways that we can having exactly X success in N child, where P is the probability of success, 1 minus P is the probability of failure. So notice that is N minus X. So this formula can be used to find probability for binomial. This is the hand computation formula. So let's plug it in, see if we get the same thing as we did before. Right? So for here, let me finish the probability here. So the 3 ways to get the same thing, to find probability of exactly 2 of them success, probability of exactly 2 success, 2S is equal to add all 3 of them together, or 3 times 0.096, because all have 3 same answers. 0.096, I'll get 0.288. That's the final answer here. The probability of having exactly 3 trees survive, if I add all 3 probability, that's what I get here. Okay? Alright, let's use the binomial formula, see if we get the same answer. Okay, to plug it in, I would have N is 3, so X is 2, X of them survive, 2. And then P is 0.4 to the power square times 1 minus P, which is 0.6, 1 minus 0.4, which is 0.6, to N minus X. N is 3, 3 minus 2 is 1. Right? So you calculate it, and you will get the same answer. Let me show you how you get it in the calculator. Okay, so here, to get to combination, first, you're going to type in 3 and go to math, go to probability. Notice that the third one is combination, so 3, and choose 2. Okay, that is 3, which is exactly how we found here. There are 3 ways having 2 S and 1 F. Now, that number, I'm going to multiply 0.4 square, 0.4 square, and then times 0.6 to the first power, which is 0.6. So the first power, we don't have to replace it. So the probability is 0.288. 0.288. which is exactly what we got in the first one here. So this formula here is called hand computation formula, right? That's for a binomial experiment. And this over here is how we did it in chapter 5, right? In chapter 5, we say this is a way of doing independent events to find probability n. We multiply, right? We multiply probability of success times probability of success times the failure, right? And using that, we say we drive to the formula for the combination and for hand computation for binomial. Well, let's do one more hand computation. Let's say I have 20 trees transplanted. What's the probability of having exactly 12 of the trees survive? Exactly 12. Notice that for 20 trees, I can't really use tree diagram anymore. Notice that how many times I need to draw the diagram to 20 trees. This is only n equal to 3 here. N equal to 20, meaning that I have 20 branches, which is almost impossible to draw. So there's limitation for tree diagram here. So we use the binomial. So let's do n is here. In this case, is 20, right? My p is probability of success, still 0.4. 1 minus p is 0.6. X is exactly 12 of them success. So 1/12 success, 12 trees survive, so 12. So calculate probability of 12, or you can also write as p of x equal to 12. You can write this way as well. And that is equal to 20 choose 12 times p 0.4 to the power of, let me use a different color, to the power of 12 times n minus 1 minus p, in this case 0.6, 0.6 to the power of n minus x. It is 20 minus 12, which is a. Notice that 12 plus a always give me 20 here. And calculate that. Here, I can calculate just using the calculator. Let me do it using calculator in one step. So first, I'm going to do the combination. So 20, go to math, go to probability. All right, go to number 3. I want 12, so 12 times 0.4 to the power of 12 times 0.6 to the power of a. Notice that you can use the little arrow here to exit the power, right? Exit exponent, and put enter. All right, so that is 0.0355. So the probability of having exactly 12 trees survive is 0.0355. Let's do one more problem for the hand computation. A student is going to take an exam but is completely unprepared. The exam consists of 20 multiple choice questions with 4 possible answers on each question, with only one answer considered correct. The student completes the exam completely by guessing. What is the probability that the student gets exactly 14 of the questions correct? Okay, so since there are 20 questions, so n equal to 20. For each question, the 4 choices, only one of the choices is correct, so 1 out of 4 is my p. 1 out of 4 is same thing as 0.25. 1 minus 0.25 gonna give me 0.75. I want exactly 14, so x is exactly 14. So now I plug it in, so n c x, n is 20, combination, I want exactly 14. Multiply p, p is 0.25 to the power of x, which is 14, times 1 minus p is 0.75 to the power of n minus x, which is 20 minus 14, which gives me 6, and calculate that. Using the calculator, I'm going to do 20 to 20 combination, go to math, go to probability. Oh, I typed in the wrong thing here. Let me do it again. Let me do 20, math, go to probability, down to number 3, and I want 14. Let me calculate that. Now multiply to p to a 0.25 to the power of 14. Exit the exponent by using the arrow, times 0.75 to the power of 6. Oh, it should be 6. and that is a very small number. Notice a negative 2.569 times e to the negative 5. That's a scientific notation, meaning that you're going to move the decimal left 5 times. So this is scientific notation, approximate 2.6 to the e to the negative 5, move decimal left 5 times, and I get 0.000026. So the probability of having getting exactly 14 questions correct for this exam, if we unprepared, chance is very low, which is unusual here. Right? So this is a hand computation. Now let's find binomial probability using calculator. Now to use the calculator has two functions that will help us find probability directly. Those functions are Binomialpdf and Binomialcdf. Both are found on the distribution menu on the calculator. Right. Binomialpdf finds the probability of exactly X success, where Binomialcdf is the second one here. This is PDF. CDF give me a probability of X or fewer success. Alright, for Binomialpdf here, I can write this as if I let X equal to K. So probability, this one is probability of X less than equal to exactly K equal to K is equal to I can do binomial PDF, and then I can enter N PX, right? Exactly. So if I want a probability of X less than equal to K, then I'm gonna do Binomialcdf and then NPX. Notice the differences here. One calculate the probability exactly 1, where the other one calculate probability of X or fewer. Right? So let's calculate the same problem using binomial formula. Here, I want to calculate probability of 14, meaning that probability X less than equal to 14. Exactly 14, I mean. So this is probably X equal to 14 here. You can write either way. Okay. So to use my calculator function, I will say binomial. Since I'm doing exactly one event, so I'll do PDF. And in this case is 20. P is 0.25 and X is 14. So on your calculator, let me take it out. Let me clear the window. Go to second vars, binomial, go down to the list, keep going, go down. Go down, down. Notice Binomialpdf is here, highlighted, enter. And number of trial is 20. And P probability of success 0.25. Keep going. And then that is something is wrong with my calculator. I think I did something wrong. Let me try again. I think somehow my calculator not correct here. Let me do it one more time. So second vars, go down to binomial. Binomial PDF, okay, 20 and enter, and 0.25 X value. I didn't put an X there, that's why 14, and then put enter. All right, so P, the first one is N, the second one is P, the third one is your X. Right, this is square. So notice that this is approximately 2.6 to a power of -5, which is exactly what we got earlier. All right, so it's 0.000026. For Binomialcdf, we need to be very careful about the wording. Right, we need to read the question very carefully, thinking CDF as X or fewer. All right, let's do some example. That said, we can use the function on other ways, or the other type problem. So this is going to do a different way of using the PDF or CDF. So let's do one problem. Assume that 13% of all airline flights at a sample 20 flights is chosen. Find each of the following. Probability exactly 4, again exactly, meaning that, let me write it. Probability of exactly 4, meaning X equal to 4. And x, the random variable is x here, and the value of x could be 25, so x could be 0, 1, 2, all the way to 20. That's a value for x. Note that 13 here is my p equal to 0.13. Right, so exactly 4, that's binomial PDF. N is is 20 flies. P is 0.13. X exactly 4, so 4. So type that in your calculator. Let's do it. So go to second vars, go down to binomial PDF. Okay, and N is 20, P is 0.13, X is 4, okay, and that's 0.1491. Let's do the second one. 6 or fewer are late. Okay, it's good practice to list out exactly what value are we talking about here. 6 or fewer meaning x equal to 0, 1, 2, all the way to 6, including 6. So 6 or fewer, that is CDF. So that is probability of x less or equal to 6. Notice that this 6 is cutting over your k. That is binomial. N is 20. P is 0.13. X is 6. And type that in your calculator, and you'll get the answer. Okay, let me clear the window. This is the first time we do CDF, so let's do it. So second vars. Right. Oh, second vars again. So go down. The CDF is one below the PDF one. Notice that this one is CDF. It's same. We enter the same value the same way. Number of trial in this case is 20. Probability of success is 0.13. And X is exact 6 or fewer, so 6. Okay. Now binomial CDF of 6 or fewer, meaning that if you do PDF, you will add PDF of 0, 1, 2, 6, add them up, you will get CDF, alright? But here, I can just do CDF. What is that? This is 0.9896, or approximately 0.9897. Okay. Now, number 3, what is the probability that fewer than A are late? Okay, let's list out the value of fewer than A. Fewer than A meaning my X value are 0, 1, 2, all the way up to 7. Notice that I'm not going to using A because fewer than A. So probability of X less than A is the same thing as probability of A less equal to 7. So probability of X less than A, this is the same thing as probability of X less than equal to 7. Notice that I'm using the 7 here because fewer using CDF. Right, so less than equal to 7, then I can CDF binomial CDF 20.13 and then 7. Type that in your calculator, you'll get the answer. For the following now, I'm just gonna list out the function instead of calculate it. Right? So let's do the number 4. Number 4, what is probability that at least 6 are late? Okay, read the word carefully. At least 6 meaning 6 or higher. Right? At least 6. So that means X value are, my X values are 6, 7, 8, 9, all the way up to 20. Okay, CDF give me less than equal to. So let's think of how I get this value. So the all possible value for X are, the possible value for X is 0, 1, 2, 3, 4, 5, 6, 7, all the way to 20. But right? So if I do CDF 20, I add everything up to 20. But I don't want to include 0 to 5. I do not want to take that out. So what I could do is I could do binomial CDF of 20, then a minus binomial CDF of 5. That will take away the 5 here. So this is what I wanted. So to take so let's do it. So binomial probability of x at least 6, meaning greater or equal to 6, is equal to probability of x. In this case, I'm going to do less than or equal to 20. Use the maximum. Notice that if it's less than or equal to 20, that's 1, right? Think of it as a complement. Let's write complement, right? Greater or equal to 6, complement of that is 1 minus the probability of x less than or equal to 5. Again, I want all the way to 20, or you can do binomial up to 20 and then minus the binomial CDF. But 20 is the total, all possible outcome is 0 to 20. So that's just 1 probability of that. So think of it as complement. To get at least 6, again 1 minus probability of x less than or equal to 5 will give me what I wanted. So to do that, I can just plug it in. I can say this is equal to 1 minus binomial CDF of 20, 0.13, and then 5. All right, so plug that in your calculator, you will get the answer. 0370 approximately. All right, let's lead out to the next one. Okay, I want more than 4. More than 4, again, let's list out the value again for the value that I wanted. So the x value that I wanted are 4, 5, more than 4, not including 4, meaning more than 4. So 4 is not included. So 5 more than 4, 6, 7, all the way to 20 again. So the one that I don't want it is 0 to 4. Again, think about the all past. So that means I can do the complement again. So probability greater than 4, not that greater than 4. You can also say greater or equal to 5 is equal to 1 minus the probability of x again less than or equal to. Okay, now that I think about what I want to take away. I want the answers from 5 up. So I want anything that's less than or equal to 4, right? Which is the complement. Now you can become the same problem as we did earlier, which is 1 minus binomial CDF of n, which is 20, 15, then 4. And then calculate that. 0.1083. Okay. Again, be careful with the wording here. Let's do number 6. At least one. The plane is going to be late. Okay. At least 1 meaning 1 or more. At least 1, right? Highlight. Let me do highlight again. So the values wanted are 1, 2, 3, 4, all the way to 20. Notice that the only one that's not included in all possible value of x is 0. So the complement is x equal to 0. Notice that if I take out the 0, that's just the complement of that, right? So x is the complement, equal to 0 is the complement of this event. So probability of at least 1, meaning is equal to 1 minus probability of x equal to 0. Notice that there's only one that's not included. 0, x equals 0 is not included. X equals 0 here, meaning that none of the plane is left. Right? So 1 minus binomial. Now here I'm going to use PDF because it's exactly one event only. So that will be 20.13 and then 0. That in your calculator. 9383. Well, last problem for this set. So what is the probability that between 6 and 9 of the planes are late? Okay, let's first list them out. Between 6 and 9 here, let's think of between here as inclusive. We can consider it is inclusive. Let's think of inclusive here. So between 6 and 9 will be 6, 7, 8, 9. I can do binomial PDF of 6 plus PDF of 7 plus PDF of 8 plus PDF of 9. That would be one way to do it. One way to do it, I add each one up, calculate using binomial PDF of 6, add them up, I get approximately 0.0370. Another way to do it is use CDF. All right. So I want to find a probability between 6 and 9. So if I do a probability of, let me write it, 6 less than or equal to 6 less than or equal to 9. If I do binomial, let me write, I erase everything. Let me do it again. So probability 6 less than or equal to x less than or equal to 9. That is equal to probability of x less than 9 minus the probability of x less than or equal to, let's think about what I wanted. I want to take away anything from 0 up to 2, so less than, right? So that is same as binomial CDF of 20.13 and 9 minus binomial CDF up to 0.13 and then subtract that, use your calculator, you get approximately the same answer. So for binomial CDF, PDF, you can use it in different ways. But be careful here, again, when you do CDF, you can use a combination of, you can use the complement rule that we learned in chapter 5. You can also think of about CDF as the x or less, or anything that's less or equal to. So you can rewrite the problem and redo it. Well, next time for chapter 6, I'm gonna make the mean and standard deviation for binomial distribution. All right, see you next time.